Hello, Dr. Peter. I'm Bishal Babu Dumre. I'm today trying to present my research background and my future plans utilizing first principles methods. So, all of the research that I'm presenting today was done in my PhD career under the advisorship of Dr. Sanjay Khare. I want to thank the funding agencies, the Air Force Research Laboratory, National Science Foundation, University of Toledo, and Ohio Supercomputer Center in order to sponsor my research and helping to realize this research. The research that I do in general is computational material science. We try to increase the efficiency of solar cells. The materials that I studied are these. So, in reality, a solar cell has many layers in it, and depending on company to company or research to research, there can be some differences in the number and the kind of the layers that goes into a solar cell. Basically, our research was focused on these two layers, the absorber layer and the transparent conductor layers. So as I just said that we were trying to increase the efficiency of solar cells, and in order to do that we definitely have to select certain materials, so we can have some material selection criteria. So in case of solar cells, the first criteria for the material selection can be thought of as the band gap. Uh, so if there is any material whose band gap is more than 3.5 electron volts, that can be used as a transparent conductor, whereas if there is a material whose band gap is between 1 and 3.5, that can be used as an absorber layer. Specifically, if the band gap is between 1 and 1.5, that is used as a single junction solar cell, whereas if the band gap is more than 1.5 up to 3.5, those materials can be used as multi-junction solar cells in tandem devices. So once we figure out the band gap of a material, uh, we have to go towards the research of absorptivity and reflectivity, because any two different materials with the same band gap may not have the same absorptivity and reflectivity. Similarly, once we think about absorptivity and reflectivity as our second material selection criteria, we again have to dive into our further research into stability, because in order to realize a material in a lab, it has to be stable. Similarly, solar cells are subjected to different real life conditions for which solar cell has to be a certain solar cell has to be of a certain hardness. Similarly, the effective mass helps us to provide the idea of mobility, carrier mobility, and diffusion length in the material, that helps us to understand the electronic and whole transportation situation inside the crystal structure. So the criteria that we just described here are only calculatable in our research, but there can be many other selection criteria which has to be thought for while selecting a material, such as cost, the availability of that material, the toxicity, and there can be many. So these are the major characteristics that we have thought about and calculated in our research. So as I just said that we do calculations to find out a certain value for a certain physical property. So we must use some methods to calculate. So the first method that we use is the density functional theory. It helps us to provide the ground state property, such as formation energy for any crystal structure. This actually solves the Schrodinger equation, which was modified by Cohn-Sam, the SI equals to E psi. WASP is the software that we use, which is based on DFT. You can also use some other software such as Quantum Espresso. Now, the excited state properties such as band gap and effective masses cannot be handled properly by density functional theory, and in that kind of situation we use hybrid theory. Hale Squizzeria Anjan Hoff HSU6 is a version of hybrid theory that we use in our research, which has 75% of density functional theory and 25% of Hartree-Fock theory. So it's a mixture, it's a blend, that's why it's called a hybrid theory. So we also use cluster expansion formalism and Monte Carlo method to calculate phase diagrams in conjunction with the DFT. I want to briefly describe density functional theory. Here we have boron atom. The green lines indicate the interaction between the nucleus and the electrons, whereas the red lines they indicate the interaction between electrons themselves. If we think about the number of interactions between nucleus and electrons only, then it will be 5 times 3 in 3 different directions. So altogether 15 different interaction terms only for the interaction between the electrons and the nucleus. Similarly, we will have some extra terms for the electron interaction as well. So instead of having so many terms for interactions, if we just think about one specific density of electrons, then all those huge number of interactions can be boiled down to simply 3 different interactions in 3 different directions between electron and between the electron density and the nucleus. So we all remember that in Schrodinger equation we have H psi equals to E psi, and the H is the Hamiltonian, which has one single potential energy term. But here we have 3 different potential energy terms. The V external is the interaction between the electron density and the nucleus, whereas V Hartree and V exchange correlation are different interactions between electrons themselves. So by using this as a Hamiltonian, we can calculate the energy of a certain crystal structure. So how we do this is, so we just said that instead of using different electrons as point particles, we can use electron density as a single entity. And since we are guessing that we are just hypothesizing that let's think about electrons as a single entity, we should guess that at first, and by guessing that and putting that into this expression, we can determine the Hamiltonian, and after that we have to solve the Cohen-Sam equation, which is the modified Schrodinger equation. It's basically an eigenvalue problem, and we get the new density after that, and we keep on iterating that new density until it converges up to a certain point, and then finally we get the energy. So that is the ground state energy, which can be used to ultimately figure out any other physical property that can be calculated by using density functional theory. So the density functional theory actually gives us only the energy, which can be further utilized to calculate other physical properties. So I want to discuss briefly 2 of the research projects that I did, just to show what kind of research I did in the past. So one of the first material is the cadmium selenium telluride. It's a well-renowned solar cell material. It's highly used in the photovoltaic market these days. The photovoltaic market is dominated around 10% by this material. So the unique idea behind our research is that we have utilized both the crystal structures while alloying this particular material. The cadmium selenium telluride, it can exist in both zinc blende and Wurtzite crystal structures. Cadmium telluride likes to form in zinc blende crystal structure normally in normal conditions, whereas cadmium selenide likes to form in Wurtzite crystal structure. We have done alloying in the range of 0 to 1 in steps of 25%. So one of our key result was the phase diagram, which I have explained in the cover letter as well. And that I personally went through a lot of hardships while calculating this particular phase diagram, and I was lucky enough and persevered a lot to get this done. So the result of this phase diagram tells us that this area in the blue does not have any mixing while the alloy is being formed until 325 kelvins of temperature. So you can mix this particular material only beyond 325 kelvins. After that, you can realize the zinc blende crystal structure in this red region, whereas you can realize woodside crystal structure in this yellow region. As you increase the temperature, you can form the alloy in woodside crystal structure even at a lower selenium concentration. Our calculation exactly matched the experimental result of the phase diagrams as well. Here we have the bowing curves for band gap. We have found that the band gap for both zinc blende and woodside crystal structures are downward bowing. For the zinc blende crystal structure at nearly 40% selenium concentration, we have found that this particular material can be used in order to realize a very high efficiency solar cell. There is a limit called Shockley-Queisser limit in solar cells, which tells that if your band gap is between 1 and 1.5, you can realize a very high efficient solar cell. So in that sense, we can say that zinc blende at nearly 40% selenium concentration can be utilized as the absorber layer in the solar cell. We have also calculated effective masses. The electron effective masses have upward bowing, whereas the hole effective masses have downward bowing. For comparison, silicon has effective mass of 1. So zinc blende crystal structure has a lower effective mass compared to silicon, whereas both the electron effective masses are lower. Whereas the woodside structure for the hole effective masses have a higher value of effective masses compared to silicon. We can expect, as we already discussed, that the zinc blende crystal structure at 40% selenium concentration can be used as the absorber layer. In that sense, the zinc blende crystal structure has a lower effective mass compared to silicon, which can be a good characteristics for this particular material to have a nicer electronic movement, a hole movement in the crystal structure. We have optical property calculations done. We can see that the zinc blende crystal structure has a better response than woodside crystal structure in the solar irradiation. The first peaks correspond always to the band gaps. As the selenium concentration increases, these peaks go to a lower value, whereas they again come back at a higher value as the band gap increases at the highest selenium concentration. The reflectivity curves are commensurate to the absorptivity curves. We have absorptivity value for silicon to be around 10 to the power 3, whereas we have absorption coefficient values for CAT-TEL cell to be 10 to the power 5. So we can say that the optical absorption for cadmium selenium telluride is better than silicon. Similarly, I am going to talk briefly about my other material, magnesium tin nitride. We got inspiration from Kawamura et al. They recently synthesized disordered rock-salt crystal structure for magnesium tin nitride, and we also thought about doing the DFT calculation for them, and we found that our value of lattice constants and the band gap, they matched with the experiment. Disordered woodside and orthorhombic crystal structures were also prevalent in the literature, so we thought about doing a comprehensive study of all these three crystal structures. And in the experiment, there was an ambiguity of oxygen incorporation. That's why we tried to incorporate oxygen into the anionic lattice and try to find out what was happening. And we found that all the band gaps, they went to zero, and they all showed metallic character. Uh, from the band gap values, we assessed that magnesium tin nitride in disordered rock-salt crystal structure can be used as an absorber material, whereas the other two crystal structures can be used as transparent conductors. Effective masses are lower for disordered rock-salt crystal structure. Formation energy is higher for the rock-salt crystal structure. Uh, we have the absorptivity curves for magnesium tin nitride as well, and the reflectivity curves. It has only one peak for disordered rock-salt crystal structure, which is corresponding to its band gap. And we also have the reflectivity curve commensurate with the absorption. If we see the value of the absorption coefficient, it's 10 to the power 4. For cadmium selenium telluride, we had 10 to the power 5. So the absorption in this particular material is lower than in cadmium selenium telluride. We have phonon calculations done for this material, and we can see that there is no any negative frequency for all these three materials, which means they are stable in lab. These can be realized in laboratory and in manufacturing facilities as well. We can see that for lighter elements, the vibrations are at a higher frequency, whereas for heavier elements like tin, we have the vibrations are at a lower frequency because they can't vibrate much. We also have some gaps in these phonon curves, which can be utilized as uh, sound frequency reflectors. So these can be used as mirrors to reflect a certain kind of sound. Similarly, we have also calculated density of states and CUHP curves for magnesium tin nitride. We have found that in all three crystal structures, nitrogen is dominant just below the Fermi level in the valence band area. In the COSP curve, we have found that there is a anti-bonding state found nearly at 4 minus 4 electron volts below the Fermi level, and this clearly tells us that the formation energy for the rock salt crystal structure is higher, which is what we saw in one of the earlier slides. Similarly, we also have calculated the band structure diagrams for two of these crystal structures. The red dots signify the conduction band minima, whereas the green dots signify valence band maxima. We can clearly see the gaps here as band gaps, and these diagrams provide us a very nice, elegant way to see how the electronic states can be prevalent in these materials. The Fermi level has been set at 0 electron volts. In a nutshell, I'm trying to show the sortings that I did based on the band gaps for all the materials that I calculated. So these materials, I have thought that these can be used as transparent conductors. These all can be used as absorber materials. So whatever the materials I did research on, I'm just trying to sort them based on the band gap. These were realized as stables, these were unstables. Similarly, I also calculated Vickers hardness for certain materials, and the values are here. So likewise, I was able to publish 10 research papers, 5 as first authored and the others as co-authored publications in my PhD career. So Python, I used Python extensively when I was parsing the data generated by the DFT, and also Python was highly used when I was creating figures, which I just showed you here in this presentation. High performance computing experience was gained while I was simulating DFT with VASP, and the simulations were done on Ohio Supercomputer Center. Ohio Supercomputer Center has a low memory node with 28 processors of 28 gigabytes and a high memory node uh, of 48 processors of each 1.5 terabyte uh, in a cluster called Owens. So they have different clusters. So this particular configuration is for Owens cluster. So I used Ohio Supercomputer Center in order to do simulation. Along with that, we also had two different clusters in our own university here at Toledo. And one of the clusters had only 24 processors. It had only one node, whereas the other one had 56 processor, two nodes. Magnesium tin nitride, I also discussed a little bit about that particular material that can exist in three different crystal structures. There is some ambiguity in literature that some of them say that this particular crystal structure can be realized easily. The other one may take some more energy. This one can be endothermic, that one can be synthesized easily. So there is some ambiguity on which particular crystal structure can be dominant, can be easily formed. So my idea was to calculate formation energy and band gap for about 100 different permutations in the crystal structure, and then apply the learned information into all the other permutations that can exist in magnesium tin nitride, so that we can find out which particular configuration will be formed with the lowest formation energy and what their corresponding band gap be. In order to do that, I wanted to use crystal graph convolution neural network. So the good thing about this particular algorithm is that we do not have to think about uh, specific descriptors. So the crystal structures are converted into graphs. The atoms are taken as nodes, whereas the nodes are connected by lines as bonds. So that's how a graph is made, and that itself is a descriptor for the crystal structure. That's why the ease of using this particular network, this particular algorithm, is that we don't have to think about descriptors. So, so that is my basic idea, to calculate formation energy for about 100 structures, learn from that, and then use it into all the other crystal structures. There are about 12,000 structures, and that's how I was trying to figure out the lowest formation energy for a certain structure that can be formed in the lab. Beyond CGCNN, we can also use other beyond CGCNN, we can also use any other algorithm by figuring out a specific descriptor and checking whether the CGCNN behaves nicely or not. So I'm not married to CGCNN. We can try any other algorithms as well. So in the future, I'm ready to work on any other field such as battery or 2D materials or thermionic devices that you work on. The basic idea of simulating using DFT is similar in any material design, such as formation energy, work function, band gap, reaction barriers. So the basic idea is the same. You just analyze it in a different context. That's why I'm ready to work in any other field beyond solar cells. I can, and also we can work in LAMP software if there is a need to calculate for a bigger system, because bigger systems demand more time in computer, which may be difficult to do, and especially while trying molecular dynamics, we may use lamps as well. So if you ask me personally, in case of solar cells, I personally want to dive into antimony selenide, antimony sulfur selenide. It's a new material with promising band gap. It can be used into tandem configuration as well. There is very less literature in that particular material, uh, and it's non-toxic. It's very cheaper. The only problem is to figure out what can be how it can be translated into industry, so that we can have a cheaper processing condition on that particular material, the antimony sulfur selenide. I want to work on that particular material into the future, uh, but I'm again ready to work in any kind of field, battery or 2D materials, or any other thing that can come along my way. I'm not that much particular about solar cells. I think that research can be done in any field, and we can contribute at any position at any field. Thank you very much. If you have any questions, please reach out to me in my email.